Properties of Logarithms Part 2. You know what? I don't know why this happened. It kind of got scooted up here, so let me move it down so you can see it a little bit better. It's a to the m over a to the n is equal to, yeah, when they have the same base and you have division, what do you do with the exponents? Hopefully you remember that you end up subtracting them. If you want to convince yourself, you could always do like a to, let's say, the 7th over a to the 4th. That's going to give me 7a, 7, I think there's there, and 4 a's, and then a set, 4 sets of a's cancel out, and I end up with a to the 3rd, which would work out the same as a to the 7 minus 4, which is a to the 3rd. So those two things are equivalent, so you can just subtract. So what do you do with the exponents? Subtract. So I want you all to remember, like I said before, logarithms are exponents. So the properties that work for exponents are the properties you use for logarithms. In the previous one, the product property of logarithms, we showed what happens when you have log base b of m times n. So now instead, when you multiply, you add exponents. When you divide, you subtract exponents. So essentially, that's what's happening here. So I want you guys, the proof for this is almost identical to the product. So the first step, if we looked at the proof for the product, was to convert to exponential form. Then instead of multiplication property of equality, it's going to be division property of equality. Instead of addition property of exponents, subtraction property of exponents. And then finally convert back to logarithms, substitute in. So I want you all to try. I just did the speed round of that. I want you to pause the video and try doing the proof on your own, modeling it on the product right now. Pause the video and come back. So what you get here, or what I have here, are all of the steps. Convert to exponential form, division property of equality. Then when you divide, what you can do with the exponents over here is subtract those two exponents that I highlighted in yellow, then convert back to logarithmic form, and then use substitution to substitute in. Remember, we defined x as log base b of m and y as log base b of n. If I was going to, just like I did before, if I was going to do an example of this, why you would need this later on, you'll see, especially when we're solving, you can either condense, that means contract into a single logarithm, or expand. Let's do an expansion one. Let's say I did log base 7 of 7 over x. I could rewrite that as log base 7 of 7 minus log base 7. As long as we're using the same base here, we're good to go. And oh wait, log base 7, what should I raise 7 to get 7 is equal to 1. So this could nicely simplify like that. So that's an expansion. I could, why don't you guys try one now? Let's say I did log base 5 of a over, let's say 10. So try expanding. Pause the video and expand and see if you get it right. You should be getting log base 5 of a minus log base 5 of 10. All right. There's another property. If you have here a power to another power, remember, hopefully you remember that you multiply, so you get a times m, a to the, not times, a m to the n times n. And if you tried with numbers, like for example, a to the 2nd raised to the 3rd, it's the same as a to the 2nd times a to the 2nd times a to the 2nd, which is the same as a to the 2 plus 2 plus 2, which is a to the 6th. So if I just multiplied the exponents, you get the same thing. So here, what do you do with the exponents? You multiply. So, oh, I don't know why this is not very clear, but this is supposed to be a times there. For all positive m, n, and b, where b can't equals 1, log base b of m to the r. So basically, you have like whatever is inside the logarithm raised to a power. You can rewrite as r times and then log base b of m. If we're going to do the proof for that, we're again start the same way. Convert to exponential form. So that's going to give me m is equal to b to the x power. Raise both sides to the exponent r, because that's what's being used in the problem. So we're going to do m raised to the r and b to the x raised to the r. And then we have the power property of exponents, which is you multiply the exponents. So here we end up with m to the r is equal to b to the r times x. Or you could write x times r. I'm putting r first just because it's convenient for later. Then we're ready to convert back. So convert to log form. All right, so then we have log base b of m to the r is equal to the exponent, which is r times x, and then substitute in. Substitution. Look, same pattern as the other ones. X was defined as log base b of m. So we have log base b of m to the r is equal to r times log base b of m. Why is that useful? Again, we can expand. So let me give you some simple examples here on the side. If I had log base 8 of x to the 5th power, you could just move that 5 out in front. So that means you can rewrite this as 5 times, whoa, I forgot the O, log base 8 of x. Those two are considered equivalent. It makes your life a little bit easier in some cases. So for example, if I had like log base 5 of 5 to the 2nd power, I want you guys to try and simplify that now. Pause the video, pull the exponent out, and see if you get a nice number. So now we have 2. I'm pulling that out in front. Log base 5 of 5. But what should I raise 5 to get 5? That's just 1. So it's 2 times 1, which is just going to equal 2.